Let h be the function defined by h of x is equal to the integral from 0 to x squared e to the x plus t dt for all real numbers x. Then h prime of 1 is equal to one of these values. Okay, so something like this, typically, you can get easily confused and caught up in applying the fundamental theorem of calculus along with other techniques of differentiation. So what I'm going to do is I'm simply going to rewrite the function h of x so that it becomes very obvious which rules of differentiation apply at which points in time. So the first thing I'm going to do, so I'm going to write this as e to the x times the integral 0 to x squared of e to the t dt. Okay. From the perspective of the variable of integration, this x is a constant, and so that, the whole constant e to the x I've just brought out in front. And now what I have is I have two functions of x being multiplied by each other. That's a function of x, and that's also a function of x. This I can differentiate very easily, and this, differentiating this is going to combine the fundamental theorem of calculus, but also the chain rule, because I don't simply have an x in the upper bound, I have a function of x in the upper bound. So I can write this as h of x is equal to the derivative of the first function times the second, plus the first function times the derivative of the second function. And the derivative of the second function, when I take a derivative of this, fundamental theorem of calculus says I substitute that into the integrand. But then I also have to multiply by the derivative of this with respect to x, which is 2x. And then I need to evaluate this at x is equal to 1. So this gives me e integral from 0 to 1 of e to the t dt plus e times 2. Okay. The integral of e to the t dt is itself. So again, just using the other version of the fundamental theorem of calculus, this gives e minus 1. And here I have 2e squared. So h prime of 1 gives e squared minus e plus 2e squared. And so I get 3 e squared minus e, and I hope that's one of the answers. It is. That's option E. Great. Yeah, so, I mean, nice little problem. Nothing that tricky, really. But, writing things, when you have a complicated integral expression like this, and you're asked about derivatives and so on, it's nice to rewrite it or break it down into sort of fundamental parts where you can apply the familiar and common rules of differentiation to each individual part and just work through the computations like that. So, nice little problem. Thanks for watching.